Hello everyone, thanks for tuning in about S1 probability. This is not going to be kind of a video about all the different methods of probability and which ones you'd use, because two of which you would have kind of done at school. So tree diagrams and kind of two-way tables, which is what this thing is here, two-way table, because it tells you two things. But what this this video is going to concentrate really on linking two-way tables and probability notation with Venn diagrams, and Venn diagrams I know are quite new. So in S1 probability you're going to be confronted with a situation that you'll either need a tree diagram for, you may need a table, or you may need a Venn diagram, or you might need a combination of the three. And that's why probability is quite fun, because you have to react to each different situation. But let's look at this thing here. So let's imagine, like in all statistics, I like to imagine that someone's opened a small business. So let's imagine, and again, before Netflix and stuff was invented, that a family has just opened up a video shop. These are the three main titles that they've got. So Love Actually, The Matrix, Terminator. Obviously nothing to do with my favourite films. And some of them are in stock to be rented, but some of them are actually being rented at the time, so they're out on loan. So you can see there are a total of 40 videos, and 21 of which are in stock, and 19 of which are currently out of stock. So what we're going to be doing is looking at, well, what's the probability of the next customer coming in, and what's the probability of them being able to pick Love Actually, let's say. So let's do that. So the probability of Love Actually being selected would be, there's a total of 15 Love Actuallys, and there's a total of 40 videos overall. So this boils down to 3/8. And if we were looking at this in terms of a Venn diagram, you can see that if this is my sample space, and by sample space I mean if we were like to contain all of our objects within this rectangle here, and this circle I'm going to let represent the event of selecting Love Actually. So within that, we know that there are 15 videos which are Love Actually videos, and everything outside of that circle is the remainder of the videos, which must be 25. So we've already started to use our Venn diagram notation here, or pictures, to identify what we're talking about here. Let's do some more. Okay, so this time I want a customer comes in, and what's the probability of them picking Love Actually, and well, actually let's go for the Matrix this time. So picking the Matrix, and it's out of stock, so i.e. it's out on loan. So what we're going to use is we're going to use this intersection notation. So we're saying probability of picking the Matrix, and so this upside down horseshoe shape means and intersection, i.e. intersection. So probability of M and the probability of it being out on loan, so O. So how do we figure that out? Well, if I look along here at my matrix column, and I look along here on my out column, I can see that 3 out of the total 40 qualify as the matrix being out on loan. But how do I represent this using a Venn diagram? Well, we can look at it like this. So let's say we take a sample space for each thing. So there's the inventory. As we said before, here's the matrix, and we know that the matrix covers 12 videos and 28 of them are not the matrix. If I have a separate one for the videos out, I know that videos out total 19. So when we're using this intersection notation here, it's like placing the two Venn diagrams on top of each other. So actually it looks like this one in blue. I've got my matrix here, this is the whole inventory, and I've got my out here, and where these two collide is where I'll shade in blue, and this is our intersection section. So let's do some more. Now I'm going to say, well, what's the probability of me not picking Terminator? Awfully written, isn't it? Okay, so not Terminator. So what I'm going to say is not Terminator, so we could write this notation-wise as being T apostrophe, T dash, or it means T complement. So T complement means not that object. So if I want P of T complement, notice that this is the same as 1 minus P of T, because our total probability is always going to add up to 1, and it can never be less than 0. So if we look at this in terms of a Venn diagram again, here's my T, here's my Terminator, which I know is 13 out of the 40, so this makes this thing 27, and we're looking at all this section outside of Terminator. So we're saying the whole sample space minus the circle is going to give us all the area that's left. So we're saying 1 minus probability of being Terminator is 13 out of 40, so I'm left with 27 out of 40, and that's my probability. And there's more. So let's go this time for an OR thing. So I want to know what's the probability of me picking Terminator or Love Actually, let's say. Well, what we can do is we can say, here's our notation again, so the probability of T union, so this union thing is horseshoe shape, this is union, and this means OR, okay? So union means OR. So T or Love Actually L, let's use our two-way table then. So we've got probability of being Terminator is 13 out of the 40, plus Love Actually is 15 out of the 40, which gives us a total of 28 over 40, which could be simplified. So if I was to look at this as being a Venn diagram, T and L are separate, aren't they? You can't pick a video which is both the Terminator and Love Actually, so it makes sense that I can just simply add these two together. Notice though, now, and we need to be real careful about this union stuff, we can't always just add it together. Notice the only reason we could this time was because these things are separate, i.e. they are what's called mutually exclusive. So, or M dot E. Because what we're saying is that their intersection is 0. You can't be a Terminator video and Love Actually video at the same time. So when you have mutually exclusive events, we're saying that T intersection L is 0, i.e. the two rings do not cross each other. Okay, now we're going to look at an OR again, but you'll see that it is not always, you can't just add them together all the time, because what you'll do is you'll double count. So let's pick Love Actually. What's the probability of being Love Actually or on loan? So picking a video which is Love Actually or picking a video which is on loan. So I'm saying probability of Love Actually or being on loan. Let's look at our two-way table. So we have probability of Love Actually is 15, so that's all this. And probability of being out on loan though is all of this. Notice that there is a 10 here which is being counted twice. If I add this together, I get 19 over 40 plus 15 over 40, which wouldn't be right because, like I say, this 10 is being considered twice. We have an intersection here, don't we? These two things are not mutually exclusive. I have Love Actually on loan, and there is an intersection here. I want the probability of L or O. So again, if I was to separate this into two Venn diagrams to see what we're talking about, so here's L, you can be L, or you can be O. So if I was to put the two things together, I would get these two rings, and the whole thing would be shaded, right? And these are sample splits, and there's L and there's O. But we have to be careful with this double counting, and hopefully you'll notice then what we need to do is remove, basically that 10 has been counted twice, we need to remove that 10. And what is that 10? Well, that is the intersection of L and O, and this is where we derive the very important addition formula in probability. So what we're saying for the addition formula is that probability of A union B is the same as probability of A, which in this case we could take as all this, plus probability of B, which we could take as all this. But like I say, we have a double counting here, so we would need to subtract probability of A intersection B. And this is a very important formula which you must remember. Okay, one last thing is, so now we're going to recognise another bit of notation which is called the given notation. So what I'm going to say is that a customer walks in, and given that the customer, so given the customer wants the matrix, let's say, what's the probability of it being on loan? Okay, so given that they want the matrix, we already know they want the matrix, what's the probability of this being on loan? Well, let's think about this. So we're saying, and let's get this notation right then, probability of given that they want the matrix, that's what this sign here means, it means given, and we want to know what the probability of it being on loan is, given that it's in the matrix. So let's think about this in terms of a Venn diagram again. So here we have the matrix, here we have on loan. So we're saying, given that this thing is the matrix, what's the probability of it being on loan at the same time? Can you see that what we've got here, we're trying to select the probability of it being on loan, knowing that we are in the matrix sphere here. So perhaps you can see that we are taking the proportion of it being on loan and being the matrix over the entire probability of being the matrix, i.e. we're zooming in on this square. In a way, I could write my sample space again. Instead of being in the inventory as it was before, we could just be looking at the matrix, and this is our on loan section here. So we're saying, what's the probability of O given M? Well, it must be the proportion of O and M all within our probability of M. So this is a really important formula as well. And this leads us to our final point of independence. So, if something is independent, then it won't matter if the thing I've picked before, the given bit, has happened. So, for example, if I roll, let's say A means roll a 6 on a dice, and let's say B means not a 6 on a dice. Well, that means that given that I've rolled a 6 on the first roll, does that affect me not rolling a 6 on the second roll? I.e., given that I rolled a 6 on the first roll, does that affect my probability of rolling a 6 or not rolling a 6 on the second roll? No, because the dice is completely independent, right? So it doesn't matter which one I rolled first. Every time is independent of each other. So what we're saying is that this thing is actually the same as the probability of B. So to make that real clear, how do we write this out? Well, we're saying if independent, the probability of B given A is still the same as probability of B intersection A. So notice that given notation is always this thing intersection this thing over the thing on the right hand side. So we've still got this, but we're saying that this is equal to the probability of B because it doesn't matter that A has happened before. It has no bearing on this, and this is really useful for problem solving. Right, so to sum up, we've got our addition formula, which says that probability of A union B is probability of A plus probability of B, minus subtract the probability of A intersection B, because remember, otherwise we would be double counting, okay? If we have a mutually exclusive event, i.e. something can't happen at the same time, then A union B must be probability of A plus probability of B, i.e. probability of A intersection B is 0 if they're mutually exclusive. Remember, you can't be the terminator and the matrix video at the same time. We have our given notation, so probability of A given B is the same as probability of A intersection B over probability of B. Remember, this is if, like, we already know B has happened, so we only have that small intersection value over the entire proportion to work with, or probability of B. That's where that comes from. If independent, though, we're saying that probability of A given B is the same as probability of A, this thing on the left, because it doesn't matter that B's happened before, it's independent of that event. And finally, probability of not A is the same as 1 minus probability of A. Remember, this is our complement notation. And one final exercise, which I would love you to pause the video and try, is to start drawing out what this stuff would look like as a Venn diagram. So I'd like you to pause the video now and have a go at drawing this as a Venn diagram. Okay, so pause it. 5, 4, 3, 2, 1, pause it, try it. Okay, so knowing that you've tried it, let's do this. So here's A and B. We're saying not A and B. So not A, everything that's not A is everything that doesn't include A, does it? But we have to have this and B section as well. So B is happening here, but we can't include our intersection because, remember, we don't want A to happen. So this must be our finished product. If we're saying not A and not B, so we want not A to happen, which, remember, not A, here's A, not A would be everything around A, and not B as well. So not B is everything around B, so nothing can be shaded inside the circles. There is our not A and not B. Similarly, let's go for this one then. So this one is not A or B. So there's A and there's B. So let's think about this again. So not A is everything in the circle, everything outside the A circle, sorry, or we want B to happen. So not A or B. Therefore, everything that can be shaded is everything but that A section, so we are including the intersection here, we are including everything in B, and we are including everything outside of B, because we're saying not A or B can happen. Finally, we've got our not A, not B. Here's A and B. So not A or not B. So not A is everything shaded, including B here, but not including the intersection. Not B is everything shaded and not the intersection. So therefore, everything must be shaded except for the intersection. That's where they both link up. And that's it. Thanks very much for watching.